All right. So now we're going to talk about moments of inertia and the kinetic energy of a system. So basically, the way that we're going to define the moment of inertia is just by looking at the kinetic energy of the system and seeing how that is going to be formulated using our formalism from the previous section from the change in angles, the dynamics of angles and with omega. So basically, what we have here is that K, the kinetic energy, is equal to 1/2 mv squared. So the total kinetic energy of a bunch of particles moving in a circle is going to be the sum of 1/2 sigma mj vj squared, which is 1/2 sigma all of the particles times r omega squared for each of the particles, which is going to be equal to uh 1/2 sum of all of the particles masses times. Oh, this is a little bit wrong. I put the parentheses on the wrong side here. Okay, chill out. uh Masses times the radius from the axis of rotation times omega squared, with all the if the all of the particles are having the same omega, are having the same angular velocity. So K is equal to I omega squared, where we defined I to be equal to square the sum of all of the masses times the radius from the center axis, uh, or the axis of rotation squared. So this is going to, as you can see, uh, this is just a factor that is going to act like mass. It's going to be the equivalent of mass for velocity, angular velocity instead of tangential velocity, because, or no, sorry, angular velocity is related to tangential velocity instead of translational velocity. So I is going to k equals 1/2 I omega squared is like k equals 1/2 mv squared, but I is the moment of inertia, and I is given by the sum of all of the masses times rj squared. All of the masses times the radius from the moment of inertia squared. So instead of just being the sum of all of the masses, it also depends on their position. Uh, what are you doing? I just want a new share. Okay. So here is the Uh, yeah, here is the moments of inertia for some common objects. I tried writing these all down, but I realized it would take more space than I have on the whiteboard. But what you should notice is that each of these has a different moment of inertia based on the how far out the mass is. So if you have a hoop versus a ring, then the hoop is just going to have moment of inertia of the total mass times the radius of squared. But if you have a ring that has some diameter, some inner and outer diameter, then it's going to be mass over 2 times r squared. Uh, yeah, it's just going to be some. mass over 2 times the first R1 squared plus R2 squared. So the average value of this R1 basically actually or the average value of R1 and R2 squared. And then if the other thing to note, so you have the hoop, which is just I equals mr squared, and then you also have this cylinder, which is basically just a hoop with uh material going all the way through the center, and then that's going to have mr squared over 2. So depending on uh how the mass is distributed, depending upon the average value of r squared for each given mass, uh, then you're going to have different moments of inertia, just depending on how the r mass is distributed. And then you're also going to have different moments of inertia based on where you're rotating the axis, or like where from where is the material rotating, uh, or the object rotating. So in this case, if you look at I equals mr squared, uh, that's the hoop rotating about its cylindrical the cylinder axis. So like a hoop rotating. Actually, since I have a pin, I'm not going to talk about the hoop. I'm just going to talk about cylinder. So the hoop rotating about its cylindrical axis would be like this. And then that is going to have a different moment of inertia than if the hoop is rotating, or not the hoop, the cylinder is rotating around and around like this, about an axis pointing through the center of the perpendicular to the length. So that's mr squared, and then over 2, and then that's going to be ml squared over 2 for the axis perpendicular to the length. So even though they're the same material, even though they're both cylinders, and both have the same properties of length and radius, that's going to they're going to have different moments of inertia, because in this case, the average radius is going to be much bigger if I'm rotating around this place this way than if I'm rotating this way, in which case the average radius is barely anything at all. So the mr squared, the sum of all of the masses times the radius from the central axis, is going to be equal to the sum of mr squared for each tiny particle. So it's going to be different depending on which axis you're moving from. So that uh, is basically the gist of moments of inertia. Now I'm just going to very briefly go over how to calculate one of these moments of inertia. And hopefully it shouldn't take too long, but you know how it is. Uh, so I, so we're going to be calculating the moment of inertia of a thin rod. rotating about the center of the rod. So rotating this way. So omega is pointing up, which means that's rotating clockwise. So it goes from negative L over 2 to L over 2, and it's too small to have a radius, or even if it does have a radius, it is going to end up not having mattering. So I equals sigma mj rj squared is going to become sum of r squared times dm, because instead of having a number of particles that you're just adding together, you're going to have a mass distribution, which is where the number of particles is so uncountably big that it just becomes a mathematical representation, or like a mathematical formula for the distribution of mass uh, per unit length. So lambda is the linear mass density equals mass divided by length. So dm is going to be equal to lambda dl, which is going to be equal to lambda dx. If we redefine, because all of this is in the x-axis, this material's in the x-axis, all of the r squared is in the x-axis. So if we redefine, oh, I think it does matter if it has a radius, so we're just going to say that it's so small that the radius is negligible. The radius of this rod, not the radius from the axis of rotation, not to uh the particle we're looking at. So I becomes from negative L over 2 to L over 2 x squared times lambda dx equals lambda times x cubed over 3 from negative L over 2 to L over 2, which is going to end up, if you do all of this, if you plug everything in, is going to end up being lambda times 1/3, as we've already had, times, let's just do it, L over 2 cubed minus negative L over 2 cubed equals lambda 1/2, 1/3 rather, times 2 L over 2 cubed equals lambda times 1/3 times 2 L cubed. My threes aren't really coming out like threes right now for some reason. Over 8, which is going to end up being 1/12 lambda L cubed, which is going to be 1/12 uh m over length times L cubed is equal to 1/12 mL squared. But what if we're talking about instead of rotation through the center axis? Uh, we talk about rotation about the edge from 0 to L. So if that's the case, then I is going to be equal to from 0 to L x squared lambda dx, because none of that's changing, equals lambda times x cubed over 3 from 0 to L is equal to lambda L cubed over 3 is equal to 1/3 mL squared. So basically, yeah, yeah. So basically what's happening is that uh as you rotate through a different axis, it's going to have a different angular momentum. It's or not angular momentum. We're not getting to that yet. I think we'll get to that next chapter. But it's going to have a different moment of inertia. So it's going to have different dynamics when we talk about how hard it is to move and how much energy it has to move. So save as PNG. This is also a consequence or a demonstration of something called the parallel axis theorem, where I equals I center of mass plus m distance from the center of mass d squared. So in this case, the center of mass is going to obviously be in the middle of the rod. And then I should also note that for all the equations that we use, for all the moments of inertia that I was looking at, uh, okay, I just had a little heart attack thinking that maybe I had forgotten to change my share back to the whiteboard, but it looks like I have. So for all of the serum masses or all of the equations that we've been doing, the mass distribution is has been constant. So it's either been constant rho, which is the uh density, or it's been constant lambda, which is the uh li uh which is the density, the linear mass density, which is the density per length. So that's just something that I want to point out, because if you have uneven mass distributions, then it's not going to follow those formulas. But in this case, I here is going to be equal to I from the center of mass, which is 1/12 ml squared plus m times L over 2 squared, which is going to be 1/12 ml squared plus 1/4 ml squared uh, equals 1/12 ml squared plus 3/12 ml squared equals 4/12 ml squared equals 1/3 ml squared. So because we rotated this axis, or we changed the axis from here at the center of mass to here uh, at the edge of the material, it's made it so that the angular momentum or I keep saying angular momentum when I mean moment of inertia. Sorry. The moment of inertia was larger by a factor of 1/4 ml squared, which is going to be what made it 1/3 ml squared rather than 1/12 ml squared, which is quite a big number. So the smallest possible I is through the center of the mass as the consequences of this. And as a consequence of this, because I center mass plus md squared is always going to be positive, and I center mass is always going to be positive. So these are both two positive numbers, but I center mass, any distance away from the center of rotation axis of that's wrong. Center of the center of mass's axis of rotation is going to be a positive value plus no matter what distance you are from the center of mass. So if that's the case, then the distance from the center of mass is going to any distance from the center of mass is going to cause there to be a change, a positive change in uh, the moment of inertia. And then also this only works for rotational axes. So if omega parallel to initial rotational axis. So if omega is parallel to the rotational axis around the center of mass, then you are going to be able to use this. So say if I'm rotating around center of mass like this versus if I'm rotating around the center of mass like this, then that's going to be something you can use the this theorem for. But if you're rotating through the center of mass like this, and then you decide to start rotating like this, then that's not going to be something that you can use it for. So it has to be parallel to the original axis of rotation, which means it has to be omega has to be pointing in the same or in the negative direction. Okay. So one more thing before I can prove this, and if you want me to, I will on Friday. But I tried to keep these lectures under 3 hours, so I'm just going to move on right now. So trash all of this. And then the last thing to notice is that K equals sigma MIRI, or I think we were using J squared times omega squared. So uh equals 1/2 I omega squared. So 1/2 sigma RJ MJ or MJ RJ squared is equal omega squared is equal to 1/2 I omega squared. But two if we have something that's made up of two moments of inertia that we recognize, then the I total is going to be equal to I1 plus I2 plus I3 plus I plus dot 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 is equal to sigma I J. So I think that's why they've been using J this chapter, just because we're talking about the moment of inertia, and that's an I. But when instead why they're using J instead of I for summation? Because if you just staple on uh I1 equals sigma MI or MJ RJ squared for object 1, and then I2 is equal to sigma MJ RJ squared for object 2, then that's going to give us a total, then adding them together is just going to give us I total equals sigma MJ RJ squared total equals sigma MJ RJ squared 1 plus MJ RJ squared 2 is equal to sigma is equal to I1 plus I2. So that's simple enough to understand. So for a quick example, I'm not going to go through it, but if we have a rod with a disc, and then this rod is length L, and this disc is R, then I total is going to be I of the rod plus I of the disc. And it's rotating about this axis. It's rotating here. Then I rod is just uh 1/3 1/3 m rod L squared, which is one of those equations that we use. But the I of the disk has to be equal to 1/2 m disk r squared uh, plus m disk times L plus R squared. Because uh, if you notice, it's not rotating about the center of the axis. So this is I about center of mass. This is the moment of inertia around the center of mass, but it's not rotating around the center of mass. It's rotating at the end of a large stick, so or a large rod. So if that's the case, then you have to add md squared for the parallel axis theorem. I don't know if I named this. I might have forgotten to, but it's the theorem that we just went over right now. So I disk equals 1/2 md r squared plus md times the distance from the axis to the center of the disk. So I total equals 1/3 m r L squared plus 1/2 m d r squared plus m d L plus r squared. And then this is an interesting problem. I think this is a problem that I'm like just looking at it right now. It seems like a problem that I find interesting and would want to put on the midterm. So uh, I'm not going to guarantee that will be, but this is the type of difficulty that you should be looking at when you're studying for the midterm. And hopefully that's going to uh, help you study and like help you understand and like just look through this. So if you have any questions, again, I have office hours on Friday. All right. One more thing, one more section, and then I'm going to be done. So I thought this was going to take like under an hour, and so far it's taking like 3 hours. So sorry.